Right, so previously we have looked at De Moivre's theorem. Okay, that's when we represented a number in complex form. A complex number in polar form, so that's cos theta plus I sine theta, and we take all that to the power of m. Okay, so what that means, we take cos of n theta plus I sine of n theta. Okay, now when we have the modulus, that's not 1. Alright, so all that means is we also multiply, we act the power onto the modulus. So whatever the value for n, okay, so if n is 2, it's going to be the modulus squared. If n is 3, it's going to be the modulus cubed. Okay, and that makes sense when we did our multiplication of complex numbers, we kept multiplying the modulus. Okay, so it's going to be the same complex number being multiplied n times, and that's why the power is there. Okay, so this is now the application really today of how to use De Moivre's theorem. So examples, simplify the following. Alright, so if z is 1 plus I, so we're just going to look at z by itself first. So we need to calculate the modulus and the argument of that. Okay, so the modular, you should see that's root 2. Okay, and the argument, okay, we should also see that as pi on 4. Because it's 1 over 1 in the first quadrant. Okay, so that's the more trivial one, of course. Okay, so z is going to be root 2 cis of pi on 4. Represent that in our polar form. Okay, so z to the power of 5 is going to be root 2 cis of pi on 4 to the power of 5. Okay, so in other words, applying this, so we bring down the power to the modulus and we also put the 5 in front of theta for your cos and sine. So it's going to equal root 2 to the power of 5 cos of 5 pi on 4 plus I sine of 5 pi on 4. Okay, so just a side note, 5 pi on 4 is what? So we've got pi on 4, which is 45. 45 times 5. 225, which is in which quadrant? Okay, so that's where we need to consider the sign for both cos and sine. Or student take calculus, so in the third quadrant, both cos and sine are negative. So we're treating it as the basic angle of pi on 4, okay, because that's halfway between 180 and 270. Okay, so your basic angle we're considering, and we use this, both will be negative because both sine and cos are negative. Okay, so root 2 all to the power of 5 is going to be 4 root 2. Okay, so we've already established cos and sine both negative in the third quadrant. What is cos of pi on 4? Yep, so negative 1 on root 2. Okay, this will actually be a negative because we know that sine's negative in the third quadrant. And what is sine of 5 pi, or what's sine pi on 4? Okay, this one works nicely because the root 2 will cancel here and here. So it's going to equal negative 4, take away 4i. Okay, so when we have the complex number 1 plus I, we have to the power of 5. Okay, so remember we multiply the modulus and we add the argument. So really we're going pi on 4 around 5 times on there, okay, from the first point, and that will be our solution there. Alright, second one. So we've got a division but we also have powers of complex numbers. Okay, so we're going to do the same sort of approach. We're going to work out this as Z1 and this as Z2, and then I'll do Z1 to the power of 4, Z2 to the power of 7, and then I'll use my division laws with complex numbers. Alright. B, just going to let Z1 is equal to 1 plus root 3i, and Z2 is going to be negative 1 plus root 3i. Okay, so we first need to calculate the modulus and the argument. Okay. Root 3 on 1, which is going to be pi on 3. So we take the tan inverse of y over x. And in the first quadrant, we've got both real and the imaginary part are both positive. The modulus Z2 is also going to be 2. 1 squared plus root 3 all squared. Yep. And the argument, so this is, we got negative signs. We need to consider which quadrant because of the negative 1. Okay, so negative 1 plus root 3, so we're in the second quadrant somewhere. Okay, so what is tan inverse of root 3? Pardon? Not negative, just the basic angle. The 60, which is what in radian? Yep, so the basic angle, pi on 3, and then an angle in the second quadrant we represent as 180. Yep, so what's the radian measure for 180? Yep, so theta can be pi, take away pi on 3, which is 2 pi on 3. Okay, so the question asked us to do Z1 to the power of 4 over Z2 to the power of 7. Okay, that was the question, so I'm setting up as a fraction. Alright, so it's going to be 2 cis of pi on 3, or to the power of 4, or over 2 cis of 2 pi on 3, or to the power of 7. Okay, so it'll be 2 to the power of 4 cos of 4 pi on 3 plus I sine 4 pi on 3 using De Moivre's theorem. And then 2 to the power of 7 cos of 14 pi on 3 plus I sine of 14 pi on 3. Okay, we really could have left just this anyway. Alright, so what we need to do is 4 pi on 3. So we pi on 3, which is 60. 60 times 4 is 240. You right? Say it again, sorry.
With the, like the, how it's cos n theta.
Yep.
Does that go onto the fraction?
What do you mean?
Like, does it come underneath the fraction as well?
What, here?
On top as well.
I'm not sure what you're asking.
N theta, like n doesn't
Yep.
come underneath the fraction, like doesn't go on the fraction.
No, because theta is the argument, remember? So we're multiplying argument by the power.
No, still, like 4 is 12 over 3. That's what I'm saying.
Yeah, but the argument is pi on 3, isn't it?
Yeah.
Yeah, so we're doing 4 times the argument.
Okay.
Yep, so 7 times the argument. The argument this time. We've got the representative fraction. Alright, now 14 over 3, so it will be over 4 pi. Okay, so what we need to do is bring it back into the 360, 2 pi domain. Okay, so we need to do, take 2 pi away until we get 14 pi on 3 back into an angle between 0 and 2 pi, sorry, so that we can work on it. Okay, so 14 over 3, take away 2. In other words, 6 over 3, so we have 8 over 3, but that's still outside our 360. So we need to 8 over 3 take away 6 over 3, and that gives us 2 over 3, and that puts us back into the correct, into a working domain. Alright, so 2 to the power of 4 over 2 to the power of 7 becomes 2 to the power of negative 3 when you do your index laws. I'm just going to write it back as this. So 4 pi on 3 all over cis of 2 pi on 3. Okay, and then when we're doing a division of two complex numbers, okay, we do the division of the modulus and we do a subtraction of the argument. Okay, so this is going to be equal to 2 to the power of negative 3, cis of 4 pi on 3, take away 2 pi on 3. Right, so now that we've got it in a working domain, 2 to the power of negative 3 cos of 2 pi on 3 plus I sine of 2 pi on 3. Morning. Yep. Okay, so what quadrant is 2 pi on 3?
Second?
Pardon?
Second?
Second, yep. So pi on 3 is 60, doubles 120. Okay, so an angle in the second quadrant is 180 degrees, take away the basic angle, which will be 60 degrees. So we're really working on the pi on 3. So all students take calculus, sine is positive and cos will be negative. Okay, so equal 2 to negative 3. So we're working on pi on 3, cos is negative, so it'll be negative cos of pi on 3, which is yep, so negative half. And sine is positive, so sine of 60 is
Root 32.
good. So 2, 3, take away 2 to the negative 1, then negative a quarter, 3 over 4.
No.
No, that's not right.
2 over 3 is 1 over 8, so it's negative 1 over 16.
Sorry?
Is it negative 1 over 16?
Yeah, it is. Oh, yeah, because of the negative. Sorry, on the bottom. Yep. Alright, so it'll be 1 over 2 to the power of 3, multiplied by those, so you have another power of 2 added with it, so 16 on the bottom. Good, and here's some wrong. Page 53, Robin. Alright, so that is how you use your de Moivre's theorem to work out the powers of a complex number. Okay, so really what this question is saying is that to the power of 4 divided by that to the power of 7 will equal negative 1 on 16 plus root 3 on 16. Oh. Okay.